Hello everyone. Today I am in this video I am going to explain quickly and briefly about the transformation, different types of transformation required for the signal processing. Okay. So, this video is very important. I will not go the detailed mathematical explanation of all the transformation, but rather I will tell you the significance of each and every transformation that has been required for the signal processing. Okay. So, to start with, this any kind of transformation, basically in case of analog system or in case of a continuous time system, is being started with the concept of integral transform. Okay. So, as per the properties of the integration, there is a property called the integral transform. So, whenever you need to transform an independent variable from to another independent variable, we need to go through an integral transform. So, suppose there is a function x of t which where the independent variable is t and the dependent is x. Now, suppose you need to transform this variable t to a new variable, say s. So, in that case we need to have a kernel function, and this kernel has to be the function of two independent variable. One is the old independent variable, that is in this case it is t, and another is the new independent variable to which you are going to transform. So, this kernel is being multiplied with your the original function x of t. Then if we integrate, and as we know the integration gives the area or the continuous summation over all time, minus infinity to infinity gives all time, and integrate it over t. So, it will give you an expression in terms of s only, that means the integral independent variable is s only. So, therefore, once you evaluate this integration, you will get an expression in terms of x which is referred as the integral transform. Now, particularly this kernel has been defined by Laplace, a mathematician who have defined this kernel as equal to e to the power minus s t for all t greater than equal to 0 and 0 for t less than 0. So, if you put it here e to the power instead of k t s, instead of k t s if you put e to the power minus s t, it becomes x of t into e to the power minus s t integration 0 to infinity. So, this is the popular definition of the Laplace transform, where this s, in case of the Laplace transform, this s is nothing but a complex variable which is being denoted as sigma plus j omega, where sigma is the DC average value of the function x of t, and omega is the frequency content of the signal x of t. So, s is sigma plus j omega. So, definitely this x of s becomes a complex quantity. So, if we represent it in a complex plane, since it is a complex quantity, so the x axis in the complex plane will be the sigma, that is the real part of the s, and y axis will be your j omega axis, that is the imaginary part of the s, that is real axis and imaginary axis. Now, the question is why we do the Laplace transform. Basically, in case of analog system or in case of any continuous time system, basically there are basically two reasons. First of all, Laplace transform makes the mathematics involved easy. So, for example, in case of any analog system, it involves a differential equation, for example, for first order or second order differential equation. So, it is quite difficult to solve the second order or third order differential equation, but if you do the Laplace transform, then that second order differential equation becomes a quadratic equation. So, I hope you understand that the quadratic equation is far simpler than that of the solution of a differential equation. That is one of the reasons why we do the Laplace transform in case of continuous system or analog system. Another important point in terms of the signals and systems or any signal processing point of view, in case of the LTI systems, as we know, the output of known LTI system, known means where you know the impulse response of the systems, the output of the system is the convolution of the input x of t along with the impulse response. Now, there is a property of the Laplace transform that the convolution is equivalent to the multiplication in Laplace transform. So, therefore, y of t, which is equal to x of t convolution h of t, becomes x of s is equal to y of s is equal to x of s into h of s, okay, where x of s is the Laplace transform of x t, y of s is the Laplace transform of y t, h of s is the Laplace transform of h t. So, therefore, y t is equal to x t convolution h t becomes y of s is equal to x of s into h of s. So, you can understand that the evaluation of the convolution is rather complicated as compared to the multiplication in Laplace domain. Another point is, from this y of s is equal to x of s into h of s, from which you can calculate h of s is equal to y of s divided by x of s, which is nothing but this h of s is nothing but the transfer function of the systems. From the transfer function, lot many analysis can be done for the system, which is rather easier as compared to time domain analysis. That is why we do Laplace transform in case of analog systems. Okay. So, this is what is about the Laplace transform, and along with it has the different properties for the Laplace transforms. Okay, linearity, time shifting, convolution, frequency shifting, then scaling, lot many different properties of the Laplace transform, which makes this mathematical tool Laplace transform further easier for application. Next, if we as we know, the sampled version of the continuous time signal is the discrete time signal. That means, if we do the sampling of this x of t on x of t, you will get the discrete time signal. Okay? Uniform sampling, say. Suppose you have done the sampling with a sampling interval of say T s or say tau, then you will get x of n T s or n tau, where tau is a uniform sampling rate. So, which is a constant. So, you can represent it as x of n. Then, if you do the Laplace transform of that sampled signal, then it becomes Z transform. So, Z transform is nothing but the discrete time Laplace transform or Laplace transform of a discrete time signal. So, where the relationship between the s and z is nothing but z is equal to e to the power, that is exponential e to the power s tau. So, where s is that Laplace transform variable s and tau is the sampling interval, and from that e to z is equal to e to the power s tau, you can calculate s is equal to 1 by tau log of z, and finally, you can get s is equal to 2 by tau 1 minus z inverse by 1 plus z inverse. So, which is called the BLT, bilinear transformation, for the mapping in between s and z. I will not go through the detail of that as of point now. So, once you define the Laplace transform of a discrete time signal or the sampled signals, finally, you can represent that x of z, that behavior, because z becomes e to the power s tau. So, it is a function of z. So, x of z becomes summation of minus infinity to infinity x of n z to the power minus n, which is here z transform, the bilateral z transform, definition of bilateral z transforms. So, definitely, since s was your complex quantity and z is equal to e to the power s tau, so it is e to the power sigma tau into e to the power j omega tau. So, therefore, z is also a complex quantity. Since z is also a complex quantity, you can represent z as something real part and imaginary part. So, z is equal to e plus j v. In the polar form, you can represent z as magnitude of z e to the power j omega, where magnitude of z is nothing but square root of e square plus v square, and omega, that is the angle or the phase part, is nothing but tan inverse of v by u. Okay. Now, as there is a forward transform, like in the Laplace also there exists an inverse Laplace transform. Similarly, in case of Z transform also, when there is a forward Z transform x of z, there exists a inverse Z transforms, which can be evaluated using a residue theorem. like x of n is 1 by 2 pi j closed contour integration, because it involves a closed path that is in the z domain. So, x of z into z to the power n minus 1 dz. Now, once again if you look at the formula of the Z transform, then you will see that it is an infinite power series. Since it is an infinite power series, there must exist some conditions for which this x of z converges. So, therefore, we must define a term called region of convergence. So, region of convergence is nothing but the range of values of z for which this x of z converges. So, whenever you define this x of z for any Z transform, you must cite the ROC, that is region of convergence, and since it is within a closed region, therefore, the inverse Z transform involves a closed contour integration. Okay. Now, as we do the Laplace transform for analog systems, similarly we do the Z transform for the discrete time systems or digital systems. Now, as I said, in case of analog systems, the system equation is mostly the differential equation in analog, and similarly in digital, the system equations is mostly the difference equation. So, in continuous time it is differential equation, and discrete time it is difference equation. So, in continuous time case, if it is a differential equation, then in Laplace domain it becomes a polynomial, that is say quadratic for second order differential equation. Similarly, in case of Z transform, for a difference equation in time will be a polynomial in Z. So, same thing again, Z transform makes the calculation easy in discrete time case, as like in the Laplace transform makes the calculation easy in continuous time case. Okay. Similarly, in case of discrete time LTI systems, the output y of n is nothing but the convolution of x of n and the impulse response h of n. So, equivalently in Z it is multiplication. So, y of z is equal to x of z plus x of z into. So, in the Z domain it is y of z is equal to x of z into h of z, and from which you can calculate h of z is equal to y of z divided by x of z, from which you will get a numerator polynomial divided by a denominator polynomial. Now, roots of the numerator polynomial for which h of z becomes in 0 are called the zeros of the transfer function h of z, and the roots of the denominator polynomial, that is d of z, for which the h of z, the transfer function h of z becomes infinite, are called the poles of the system. So, by analyzing poles and the zeros of the systems, you can analyze lot many things about the system. So, that makes it easy to analyze the system in Z domain rather than the time domain. And further, if we design the systems, we can design the systems directly from the h of z. That is easier than designing a systems from the time domain difference equation in case of a discrete time system. That is why we do Z transform. So, that is the significance of the Z transforms. And again, as like the Laplace transform, there are different properties of the Z transforms, like linearity, then time shifting, then scaling, convolution, correlation, inversion, time reversal. Lot many different properties are there, which makes further the Z transform easier. Actually, properties makes easier. Now, coming to the another transform Fourier. Okay, as Fourier analysis, as a whole Fourier analysis. Okay, so what is Fourier analysis? It is basically a tool. This as a whole, the Fourier analysis is basically a mathematical tool which will transform a time domain quantity or function or signal into its equivalent frequency domain quantity or function. Now, why we should do? Again, it is a kind of transformation like Laplace or Z in discrete time, Z in the continuous time Laplace. Now, thing is that why we do, first of all, what is Fourier? So, this is the analysis named after the French mathematician J. Fourier, Joseph J. Fourier, and actually he had carried out one experiment during 1822 on the flow of emission of heat, and out of which he concluded that any periodic radiation or any periodic signal can be represented by an infinite numbers of harmonics or sinusoid, infinite number of sinusoid with harmonically related frequencies. So, J.B.J. Fourier experimented one heat related experiment, emission of heat experiment, from which he found that any periodic radiation or any kind of periodic function can be represented as infinite numbers of summation of infinite numbers of sinusoid with harmonically related frequencies. So, harmonically related frequencies is nothing but integral multiple of fundamental frequency. Later on, there is another mathematician called Dirichlet. He add on something with the Fourier. Initially, Fourier told that if a signal or a function is periodic, then only we can represent the signal or the function as an infinite summation of infinite harmonics with or infinite sinusoid with harmonically related frequencies. Later, in Dirichlet add-ons that along with the periodic, I mean a signal once it is periodic or a function when it is periodic, it has also follow certain conditions. Number one, the function must be single valued elsewhere. That means the function, whatever be the periodic function, that must have a well defined mathematical definition over one time period. Then second condition is that over one time period the signal must have finite numbers of discontinuity. And number three, the over one time period the signal must have finite numbers of maxima and minima. And number four is the signal must have finite DC average value. Okay. So, once a periodic signal follows these four conditions, that is finite numbers of discontinuities over one time period, finite number of maxima and minima over one time period, finite number of DC average value over one time period, and well defined mathematical definition. These four, once these four conditions, also called the Dirichlet conditions, are exist, then a periodic function is nothing but which repeats after its after certain time repeat itself after a certain time in interval. So, for example, if f of t is a periodic function, then E is equal to f of t plus t, where t is a periodic time, 1 by t is the frequency. So, once the signal is periodic and also follows the four Dirichlet condition, then as per the Fourier, J.B.J. Fourier, that it can be represented as a summation of infinite numbers of sinusoid with harmonically related frequencies. That means, it can be represented like f of t is equal to a naught plus a1 cos of omega t, a2 cos of twice omega t plus the a3 cos of thrice omega t, like that, and plus b1 sin of omega t, b2 sin of twice omega t, like that. So, where omega is your fundamental frequency, that is 2 pi f, f is equal to 1 by t. So, 1 omega t, 2 omega t, 3 omega t, like that, and for a naught cos of 0 omega t. So, that means cos of 0 is 1, and for b naught sin of 0 is 0. So, therefore, there is no b naught term, and a naught is independent of frequency. So, where it is a naught, a1, a2, a3 dot 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 b1, b2, b3, these are called the Fourier series coefficient. Now, the same thing can be summarized like this: f of t is equal to a naught, since a naught is frequency independent, then plus summation over 1 to infinity a n cos of n omega t plus b n sin of n omega t. Okay. Now, while you are going to represent a signal in terms of infinite numbers of harmonics with sinusoid with harmonically related frequencies, you must have this coefficient a naught, a n, b n. So, to evaluate these coefficients, you must apply the orthogonality properties of the sinusoid. So, orthogonality properties of the sinusoids are nothing but sine or cosine over one time period. If you integrate 0 to t sin of t or cos of t, dt is equal to 0. Then sine into cos over one time period, if you integrate, it is 0, cos into sine also 0, but sine square or cos square, then it is t by 2. So, applying those orthogonality property of sinusoid, we can find the coefficient a naught as 1 by t, 0 to t f of t dt, a n as 2 by So, here A naught is 1 by t 0 to t f of t dt. Similarly, you can get A n is equal to 2 by t 0 to t f of t cos of n omega t, and B n is 2 by t 0 to t f of t sin of n omega t dt. So, now as we look at this A naught, which is nothing but from this, it is the function f of t dt integration. So, it is area under the f of t over one time period 0 to t, n is being divided by t. So, it is the average. So, therefore, as I mentioned, A naught is nothing but DC average value of the function f of t. Okay. A n and B n are the coefficient. So, next, as you see in this the definition of the Fourier series expansion, there is no phase term. So, signal also employed with a phase term. So, if we further modify this Fourier series expansion with a phase term, then this A naught is equal to say C naught, and where C n is nothing but square root of A n square plus B n square, and theta n is nothing but tan inverse of B by n. So, then this can be summarized like this: f of t C naught plus n is equal to 1 to infinity C n cos of n omega t plus phi n. So, this n omega t plus phi theta n. Okay. So, where C n is this and theta n is this. So, this is what is called the alternative form of the Fourier series expansion, trigonometric form of the Fourier series expansion with the incorporation of the phase term. Now, further in this Fourier series expression, if we represent this cos and sine in terms of the exponential, say cos of n omega t is e to the power j n omega t plus e to the power minus j n omega t by 2, and sine of n omega t is e to the power j n omega t minus e to the power minus j n omega t divided by 2j, and do the mathematical simplification, then we will come up with this expression. Okay. So, it is simply representing cos and sine in terms of exponential function. So, then ultimately after mathematical simplification, it will come out to be minus infinity infinity C n e to the power j n omega naught j n omega t. So, where the C n is the Fourier series coefficient in this form of Fourier series, which is called the exponential form of Fourier series. So, now C n throughout the derivation, if you will get the C n is nothing but half of A n minus j B n. Now, if you put the formulas of A n from this and B n from this into this, then you will come out with this C n. Or you can do one thing, you can multiply both sides with e to the power minus j omega minus j n omega t in this function, and then integrate over 1 by over 0 to t, then you will get this. This is the Fourier series coefficient in exponential form of Fourier series. Now, so this is the briefly about the Fourier series. Now, why we do Fourier analysis? Okay. So, why we do Fourier analysis? Basically, as I mentioned at the beginning, that the Fourier analysis is for transforming a signal from time domain to its equivalent frequency domain. So, why we do it? Why we need it? First of all, a signal, while I am representing it in time domain, the information that you will get is with respect to time only. That means, time domain information only, but it does not mean that it does not have any frequency domain information too. So, therefore, we need that frequency domain information as well for the better processing of the signal. The frequency domain information was there in the time domain, but it was hidden. So, we need to extract those hidden information in time domain. So, that means, frequency domain informations are hidden in time domain. So, therefore, we need to extract those hidden information from the time domain, and we will represent it in frequency domain. As like in the time domain signal x t, where x axis is time, y axis is x t. So, that means, something is varies with respect to t. Now, while we transform it to the frequency domain, the x axis becomes the frequency and y axis becomes the magnitude in terms of the magnitude, energy, power in terms of the frequency. So, you will get the frequency domain informations. It is something like, as we know that the white light consists of all the VIBGYORs, 7 different colors, but unless you have a prism, at least a prism, you can't say, you can distinguish those 7 different colors of the white light. So, once you allow the white light to pass through a prism, it will give you the spectrum of the 7 different colors with different intensities. So, that means, the 7 different colors Vibgyor was hidden in the white light. Once you allow the white light to pass through a prism, at the end of the prism you will get the spectrum of the 7 different color with different intensity of all the Vibgyor. So, therefore, we can consider the white light as your any signals in time domain, prism as your Fourier analysis, and output of the prism you can consider as a spectrum or spectral analysis of the signal. So, that is why we do Fourier analysis, or it is something like okay. So, therefore, in case of the Fourier series, which is basically hold for periodic signal only, in that case once you represent it in Fourier series expansion, like in this form or in this form or in exponential form, in this form or in exponential form. In these forms you are representing the signals in a Fourier series expansion, but remember this form does not give you the spectral information, it just represents the signal in infinite numbers of harmonic sinusoids with harmonically related frequencies, but not yet it gives you the frequency domain information. So, therefore, once you get this expression, so if you look at this expression, this is the function f of t into e to the power minus j n omega t, sorry here it is there is a dt. Okay. So, e to the power minus j omega t n omega t dt and integrated over 0 to t 1 by t. So, now you can think of like, suppose there is a wall in front of you and behind the wall there are some things which are hidden, So, there is a wall and behind the wall there are something which is right now hidden. To get the hidden things or to see those hidden things, what you need to do is you need to break the wall and need to put a window, or simply need to put a window over the wall, so as to see the things behind the wall. So, with that analogy, if you compare this function as a window function e to the power minus j omega, where the variable is omega and t, then f of t is your given function. In that given function, suppose this window is being fixed. Okay. So, whatever be the things you have seen, that is integrating and take it out. So, integrating is nothing but that take the summation, continuous summation 0 to t over 1 time period, because it is periodic function, because same thing is repeating after each and every period. So, over one period you have integrated, that means whatever be the things through the window you have seen, all are put together and it is being divided by t. So, that means it is normalized, and due to the presence of this n is nothing but a discrete integer. So, this C n is first of all discrete, second it is normalized because it is 1 by t spectrum, and third one is periodic because it is over one period, spectrum of a periodic function. So, C n is discrete normalized periodic spectrum, frequency spectrum of a periodic continuous time signal. Okay. So, this only give you the spectrum, that is the frequency domain information of a periodic signal, which is discrete normalized periodic spectrum of a continuous time periodic signal f of t. Okay. Now, this will give you the spectrum of periodic signal. Now, what about the aperiodic signal? Aperiodic signal means which does not repeat after every time period, that means it f of t is not equal to f of t plus t. So, in that case we can define an aperiodic signal as a limiting case of the periodic signal. That means, if we put limit capital T tends to infinity to a periodic signal x of t, then it becomes a periodic signal. So, if we impose that limit t tends to infinity, then this right hand side part becomes this. So, x of t, this x of t, here instead of f of t I am writing x of t, e to the power minus j omega t, since it was discrete, but now it becomes a continuous. So, there is no n, and since it is aperiodic and t tends to infinity, so it becomes for all time minus infinity to infinity, and there is no question of dividing by t. So, n is being represented denoted as x of j omega. So, which is the continuous time Fourier transform, CTFT, continuous time Fourier transform. The definition of the continuous time Fourier transform is x of j omega integration minus infinity to infinity x of t to the power minus j omega t dt. Okay. So, I hope it is clear why we do this Fourier transform, to get the hidden information, the frequency domain information which were hidden in time domain. Once you do this, you will get the frequency domain information. This is also like an integral transform in terms of mathematics. Okay. So, this omega is your frequency, putting j to represent it as a complex quantity. So, it is a complex quantity. Now, if we multiply both sides with e to the power j omega t, e to the power plus j omega t, and integrate over minus pi to pi, because once it is a frequency, it becomes from minus in pi to pi. Sorry, it will be minus infinity to infinity. In discrete time only, it will be minus pi to pi. Okay. So, x of t becomes 1 by 2 pi minus infinity to infinity x of j omega into e to the power j omega t d omega. So, this is the inverse Fourier transform in case of continuous time case. So, if you look at this x of j omega, which is the continuous spectrum of a continuous time aperiodic signal. Okay. So, this is about the continuous time case, continuous time Fourier series and continuous time Fourier transform. Now, in case of discrete time, as like Zap transform, in case of discrete time, the periodic signal is defined like this, x of n, like a x of t is defined as x of t plus x of t, x of f of t is equal to f of t plus capital T. Similarly, discrete time periodic signal is being represented as x of n is equal to x of n plus k n, which is periodic. K is an integer, n is the number of sample. In discrete time, once it is sampled, it is no longer this time is in second, it is being represented by a integer only. So, therefore, this n is not time in second as like capital T, it is number of samples over which it is periodic, and k is an integer. So, integer multiple, say x of n plus n is equal to x of n plus twice n is equal to x of n plus twice n, like that. Okay. So, as like this exponential form of Fourier series, f of t is equal to minus infinity to infinity c n e to the power minus j omega n. Similarly, you can have the Fourier series expansion for the discrete time x periodic signal x of n. After following the Dirichlet conditions, you will get this k is equal to 0 to n minus 1 c k e to the power j 2 pi by n, because it is sampled. 2 pi is the total range, because once it is discrete time, it becomes within a circle, and within a circle the maximum frequency will be twice pi. So, twice pi n is the number of samples into k n. Okay. Now, if we multiply both sides of this equation by e to the power minus j 2 pi by n into k n and do the summation for all n, then you will get this c k. So, where this c k is the Fourier series coefficient for the discrete time Fourier series expansion of this x of n. Now, as compared to this c n, as I explained that this c n gives you the discrete normalized periodic spectrum of a periodic signal f of t. Similarly, this c k gives you discrete normalized, because it is also divided by n, discrete normalized periodic spectrum of the periodic signal x of n. Okay. This does not give you the spectrum, this is just the expansion, and this will give you the spectrum. Okay. Now, as I have mentioned, this Laplace of Fourier, the Laplace of the transform has different properties. Almost all the same properties will be applicable for the Fourier as well. obviously the mathematical expression will be different. So, in case of the Fourier series, if we apply the properties, then remember the Fourier series properties will be applicable to the Cn in case of continuous time Fourier series, and in case of continuous time Fourier transform, the properties are applicable to x of j omega. Similarly, for the DTFS, the properties are applicable for Ck. Similarly, if we compare the CTFT, continuous time Fourier transform, which was continuous time, that is the integration, same way if it is discrete time, it is summation minus infinity to infinity x of n e to the power minus j omega n instead of e to the power minus j omega t, and it was represented as x of j omega, since in case of continuous time frequency ranges from minus infinity to infinity, but in while it is a discrete time, the frequency ranges from 0 to 2 pi or minus pi to pi. So, it is within a circle. So, therefore, it is denoted as x of e to the power j omega, not only j omega. E to the power j omega, as you know, the magnitude is 1, which is a unit radius circle centered at origin in the complex plane. Okay. So, this is the definition of the DTFT. DTFT, discrete time Fourier transform. Similarly, if we multiply both sides of this by e to the power plus j omega n and integrate over 0 to 2 pi, because this, although it is a discrete time Fourier transform, but this x of e to the power j omega, remember this x of e to the power j omega is here continuous in frequency. So, the range of frequency is 0 to 2 pi or minus pi to pi. Range is finite, minus pi to pi or 0 to 2 pi, but within that finite range it is within a circle. So, within this circle, this x of e to the power j omega is continuous, okay, continuous, not in time, continuous in frequency. So, therefore, integration involved here while evaluating the inverse Fourier transform, inverse DTFT, IDTFT, inverse discrete time Fourier transform, which is 1 by 2 pi integration 0 to 2 pi or minus pi 2 pi x of e to the power j omega into e to the power j omega and d omega. Okay. So, this is what is DTFT, discrete time Fourier transform. So, here also you can compare with the previous analogy that this e to the power minus j omega n can be considered as a window function, and that window is placed over the periodic signal x of n or non-stationary signal x of n. Whatever be the things you have seen through this window over on this signal, you are taking the summation for all n all time, and that gives you the spectrum. Okay. So, up till this is the mathematical tool DTFT. Now, coming to the computing or computation of this DTFT in machines, in computer algorithms or in any machine. Now, if we look at this, expression, as I mentioned, x of e to the power j omega is a continuous spectrum over the range minus pi to pi or 0 to 2 pi within a circle, okay, within a circle. So, obviously, you can understand that this cannot be computed in a finite machine or in a computer algorithm, because it has an infinite number of samples, frequency samples over minus pi to pi or 0 to 2 pi in the frequency plane, in the complex plane. So, therefore, for evaluating or computing in a machine, we must sample it, as like in continuous time signal, it has an infinite number of sample over the time of interest. We do the sampling to make it discrete time, to make it finite numbers of samples. Similarly, this x of e to the power j omega is continuous over the range minus pi to pi. So, we need to do the sampling, because it is continuous means it has an infinite number of samples, frequency samples in between minus pi to pi or 0 to 2 pi. So, therefore, we need to do the sampling. Okay. So, suppose that omega, the maximum range is 2 pi. So, maximum frequency is 2 pi. Now, suppose I need capital N numbers of equally spaced sample out of the infinite number of frequency samples over the range 0 to 2 pi. Suppose I need n, capital N number of equally spaced samples. So, therefore, frequency content of each sample will be 2 pi by n into some constant integer k, okay, because 2 pi is the total number of maximum frequency range 2 pi, n number of samples I need equally spaced. So 1 2 pi by n, 2 2 pi by n, 3 2 pi by n, 4 2 pi by n, like that. Each sample will be 2 pi by n into k. So instead of this omega, now it is being sampled with equally spaced 2 pi by n into k number of samples. So instead of omega, I have put 2 pi by n into k. So instead of minus j omega n, now it becomes e to the power minus j 2 pi by capital N into k into n, x of n. Now since out of the infinite number of frequency samples in the frequency range 0 to 2 pi of x of e to the power j omega, you have taken n equally spaced sample. So that x of n should be a periodic extension of a finite numbers of samples. So therefore, instead of this minus infinity to infinity, this summation becomes 0 to n minus 1. And since this frequency 0 to 2 pi is being sampled an equally spaced sample, so each samples ultimately of equal that range, that is 2 pi by n. So therefore, it is being better to denoted by the integer k only, that is 1 2 pi by n, 2 pi by n, 3 2 pi by n. So therefore, instead of this e to the power j omega, it is being denoted by k only. Okay. So therefore, this formulation of DTFT, which was theoretical only for computing in a finite machine or in a computer algorithm, it is being modified as this. Okay. So which is called DFT, discrete Fourier transform. So DFT, what is DFT? DFT is nothing but DTFT only, but sampled version of DTFT, because x of e to the power j omega, that is DTFT, is continuous over the period over the range 0 to 2 pi. That means it has infinite number of frequency samples over 0 to 2 pi frequency. Therefore, we need to make it finite number of samples. So DFT is nothing but n, capital N number of equally spaced samples of DTFT x of e to the power j omega, nothing else. So this is the DFT. Okay. So this gives you the spectrum of a finite length signal x of n. Remember, while doing the DFT, it has to be a finite length. And once you do the IDFT, inverse DFT, both side multiplied by e to the power plus j 2 pi by n into k into n, and sum over all k, you will get x of n like this. So this x of n will be periodic extension of that x of n. Okay. So this is the IDFT, inverse discrete Fourier transform. Okay. Now if we relate as like this Laplace and Fourier I mentioned, this S equal to sigma plus j omega. If we look at the Fourier transform formula, if we consider that sigma is to be 0, that is this average value is 0, then S is equal to j omega. So in this formula, if we put S is equal to j omega, that becomes the continuous time Fourier transform. Similarly, in case of the Z transform, as you have seen, this complex Z is nothing but modulus of Z e to the power j omega. So if suppose this modulus of j omega, modulus of Z, magnitude of Z is equal to 1, then what will be Z? Z is equal to e to the power j omega. So if we replace this Z by e to the power j omega, then it becomes the DTFT. So therefore, if we replace Z is equal to e to the power j omega in the Z transform, that becomes the DTFT of the same signal. Now point is that what is Z is equal to e to the power j omega? Z is equal to this e to the power j omega means Z is equal, modulus of Z, magnitude of Z is equal to 1. What does it mean? If modulus of Z is equal to 1, that means in the Z plane, the circle that was centered at origin out of the Z transform will have the radius 1. Modulus of Z is equal to 1 is nothing but the equation of a circle centered at origin with radius 1, unit radius circle centered at origin. So therefore, Z is equal to e to the power j omega means Z is equal to 1 into e to the power j omega. That means if we evaluate Z transform only on the unit radius circle, that is the ROC, for the Z transform, then it is nothing but the DTFT of the signal. Okay. So, the relationship between the Z and DTFT is Z replaced by e to the power j omega, that means Z transform evaluated on unit radius circle is the DTFT. But thing is that there is a condition. Suppose once you evaluate the Z transform and that Z transform does in the ROC of that Z transform does not include the unit radius circle, then you can't evaluate that Z transform over unit radius circle, and hence DTFT of that signal for which Z transform does not include the unit radius circle, DTFT does not exist. So, remember that. Okay. So, DTFT and DFT, the relationship is Z is equal to e to the power j omega, that means Z transform evaluated on unit radius circle is the DTFT. Now, DFT, what is DFT? DFT is nothing but the sampled version of the DTFT and capital N equal space sample of the DFT. Now, if we relate it with the Z transform, so Z transform evaluated on unit radius circle is the DTFT. Now, on that unit radius circle, if you take N equal space samples, then that becomes the DFT. So, DFT is nothing but the N equal space sample of the unit radius circle of the Z transform. That means, Z transform evaluated on Z transform evaluated on unit radius circle and then take a capital N number of equal space samples over the unit radius circle, then it becomes the DFT. Or mathematically, if we replace Z is equal to e to the power minus j 2 pi by n into k, then that becomes DFT. So, Z replaced by e to the power minus j 2 pi by n is nothing but modulus of Z or magnitude of Z is equal to 1, and instead of e to the power j omega, instead of Z to the power minus n, Z is being replaced by e to the power minus j 2 pi by n. So, it is n equal space sample of the unit radius circle. So, that is the relationship between Z and DFT. So, therefore, up till this is the DFT. Okay. So, actually the mathematically theoretically up till DTFT only. So, Fourier gives you the spectrum which was hidden in the time domain, and Z gives you the transfer function, or the Laplace gives you the transfer function, which makes the calculation easy or design easy, analysis easy, and Fourier gives you the frequency analysis. Okay. Now, why we have done this DFT? Just for sake of computing in finite machine or any computer algorithms. So, while doing so, it is important to look at the computational complexity involved in the computation or direct computation of DFT. As you can see, this is a complex quantity e to the power minus j 2 pi by n k n, because it is cos of 2 pi by n k n a minus j sin of 2 pi by n k n. So, it is a complex. In multiplying x of n may be complex or real, I mean real or complex, real or imaginary or complex. So, and this is the range of n. So, this is for each k, this is for each k, this k is also here k is also same range 0, 1, 2 up till n minus 1. So, for each k n numbers of multiplication, complex multiplication, and for all k n square complex multiplication, right, capital N square complex multiplication. Then for each k n minus 1 number of summation here, as you look at this summation, after multiplication it gets summed up. So, for each k n minus 1 sum, then for all k n into capital N whole into n minus 1 number of summation. So, therefore, if we look at the direct computation of this DFT involves capital N square complex multiplication and capital N into n minus 1 capital N minus 1 complex addition. So, this means the computational complexity involved in direct computation of DFT. Also, that is one point. Also, if we look at this term e to the power minus j 2 pi by n, if we replace it with a w n, which we used to call it as Tweedle factor, which is e to the power minus j 2 pi by n, which follows actually the symmetry and periodicity. It is symmetric as well as periodic. But in the direct computation of DFT, that property which is symmetric, that means symmetric means that W n k, W n to the power k is equal to W n to the power minus k or W minus n to the power k, and periodic means W n plus so W n k, k plus capital N is equal to W n. So, this W n is symmetric as well as periodic, but in the direct computation of DFT, that two properties are not taken into consideration. That means, the advantage of this periodicity and symmetry is not incorporated in this. So, two things, it has n square complex multiplication and n into n minus 1 complex addition, along with this Tweedle factor, which is nothing but e to the power minus j 2 pi by n, is symmetric and periodic, which is not incorporated in this direct computation of DFT. So, then people have thought of like Tukey and Cooley. They proposed an algorithm for fastest computation of this DFT. That means, for reducing the computational complexity along with the incorporation of the symmetry and periodicity property of this, which is FFT. Okay, which is FFT. These two are in terms of the W n k. Okay, so if you look at this n square complex multiplication and n into n minus 1 complex addition are involved in the direct computation of DFT as well as IDFT as well. So, that is what I have written. For each value of k, the direct computation of x k involves n complex multiplication and n minus 1 complex addition. Hence, to compute for all n values of DFT, n square, this is n square complex multiplication and n into n minus 1 complex additions are required. That matches the computational complexity. Along with W n k is symmetric and periodic, which is also not incorporated in the direct computation of DFT. So, together J. W. Cooley and J. W. Tukey, they together proposed an algorithm called FFT, fast Fourier transform. So, this fast Fourier transform is nothing but a computer algorithm for the efficient calculation of DFT. Okay, fastest computation of the DFT. Okay, so here I am not going to explain this FFT. FFT is nothing but fast Fourier transform. It is nothing but your algorithm, computer algorithm. And there are two types of algorithm for FFT. One is called DIT. DIT means decimation in time. So, decimation means breaking. So, what decimation in time? So, what is there here is in time, it is x of n. So, you need to decimate that x of n. How to decimate? In terms of even and odd numbered component samples of x of n. So, it is something like this. Say for example, x of n is equal to say 1, 2, 5, 7, 8, 9, 5, 4. Suppose 8 samples wanted. Suppose these 8 samples. Okay. Suppose 8 point DFT, because one more thing, this capital N, as I mentioned in the DFT, this n has to be a power of 2, because finally it is the digital computation, or the n has to be power of 2. Theoretically, you can calculate the n with any n, that is 5, 7, 9 also, but practically that n, capital N, must be a power of 2, that means 2, 4, 8 like that. So, as many as n, that many will be the number of samples. If the number of sample is less than n, you have to add extra zeros to make it equal to n, otherwise aliasing will occur. Why? Because as in the time domain sampling, if f of s is that sampling frequency is less than the twice of f of m, then aliasing occurs. Similarly, if say L, capital L is the number of sample in x of n and capital N is the endpoint DFT. If n is less than L, then aliasing will occur in time. In case of time domain sampling, aliasing is occurred in frequency, and in frequency, because DFT is the frequency domain sampling of the TFT. So, if capital N is less than capital L, where L is the number of sample in x of n and n is the endpoint DFT. If n is less than L, then aliasing will occur. Now, if L is less than n, then while doing DFT you must add the zeros at the rightmost of the signal, which will in that case the spectrum will remain same, the only thing is resolution will improve. Okay. Now, in the DIT algorithm, so it is decimation in time. So, we need to do the decimation here in the x of n. So, how to do the decimation? So, this is at sample at n is equal to 0, n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5, n is equal to 6, n is equal to 7. Now, while decimated, first level decimation is in its even numbered and odd numbered samples. So, even numbered sample is this, this, this and this. So, 0, 2, 4, 6. So, that is even numbered samples, not even samples, even numbered samples, and similarly odd numbered of samples. So, 2, 7, 9, 6, these are odd numbered samples. So, the 8-point signals was now divided in 4.4 points. So, each of these 4 point is odd number, even numbered and odd numbered. So, 4 point next you do the n by 2 point DFT. Instead of doing 8 point DFT directly, now you are doing 4 point DFT, 4 point DFT, 4 point DFT for even numbered sample of x of n and 4 point DFT for odd numbered of sample x of n. If you do it using the direct formula, you will see that the computational complexity will reduce almost half. Further again, if you do the further decimation, second level decimation in each of the even numbered and odd numbered component, further if you divide again odd numbered and even numbered in each, then it will, the computational complexity reduces by 1 by 4 and so on and so forth. That is the DIT algorithm. In my next video lecture, I will explain in detail about this. Here actually I am summarizing the entire transform, that is why I am not going to explain all the detail of this. Similarly, DIF is the decimation in frequency. So, decimation in frequency means what you are going to decimate? You are going to decimate x of k as same way, and that is, it is a back calculation. So, x of k is in each odd numbered and even numbered values samples. Okay, that way decimation in frequency. So, in case of 8 point, 3 level of decimations, 2 to the power 3 is 8. So, in each after 3 level of decimation, you will not get any complex multiplication. So, the computational complexity gets reduced. Okay. So, this is what is FFT. Hope up till this is clear to you. So, Laplace in continuous time case for making the calculation easy, for system design, for analysis the system in terms of poles and zeros and all. Similar is the Z transform in discrete time case, and Fourier in the TF Fourier series or Fourier transform. Fourier series is for the periodic signal, Fourier transform is for the periodic signal, both in discrete continuous time and discrete time, to get the spectrum. Okay, to get the spectrum. Hope it is clear. Now, we will go to the another relationship of DTFT or DFT. So, if you look at this DFT formula, again x of k is this, So, in this formula, this e to the power minus j 2 pi by n k n is a complex quantity. So, since it is a complex quantity, it can be represented as cos of 2 pi by n k n minus j sin of 2 pi by n k n. Now, if I consider only cos part, then this x k becomes real only, right. That imaginary part I have neglected, right. This is suppose e to the power j theta, that means that cos of theta minus j sin of theta, e to the power minus j theta means cos of theta minus j sin of theta. So, if I am considering only cos theta out of that cos of theta minus j sin of theta, then that becomes the real part. Okay. So, that is what is called discrete cosine transform, DCT. Okay. So, discrete cosine transform is actually expressed as a sequence x of n in terms of a sum of say cosine functions of different frequencies and amplitudes. It is like a DFT, a DCT, that means discrete time cosine transforms operates on a sequence at a finite numbers of discrete data points. Okay. So, basic distinctions difference between DCT and DFT is that in DCT uses only the cosine terms, while in the DFT it uses both cosine and sine terms. So, basically this DCT is widely used for the wide applications like image processing, image compression, video processing, video compressions, also audio applications, basically for the compressions, and this DCT is being selected as a significant part of the various international standards like JPEG, Joint Photographic Expert Group, like MPEG, H261, H263, these are compression techniques. Okay. Also, there are primarily the advantage of DCTs are, number one, the DCT coefficients are purely real, as I mentioned, because it involves only the cos terms. And another second advantage of the DCT, that it has near optimal property for the energy compaction, compactness. And third, DCT can be computed efficiently using fast algorithm like FFT. So, as a result, this DCT is used extensively in the signal processing and particularly image and audio processing and image and audio compression. Okay. So, therefore, DCT is nothing but the real part of the DFT, and actually it is a real and even part of a real and even sequence. So, discrete cosine transforms are equivalent to DFT only, but roughly twice the length of the DFT, which is being operated on real data, because it is real part. So, it is being operated on the real data with even symmetry. So, remember this, DCT is nothing but the DFTs only, but taken roughly twice the length, that is that of the DFT, and operating on real data, that is x of n real, with even symmetry, that means x of n is equal to x of minus n. So, depending on the symmetric, that the even symmetric symmetric extension of x of n, depending on various symmetric extension of x of n, different DCTs are there. Okay. Different DCTs are there. So, those DCTs are known as DCT 1, DCT 2, DCT 3 and DCT 4. Out of these 4 DCT, DCT 1, DCT 2, DCT 3, DCT 4, the most popular DCT is DCT 2, and this is also known as even symmetric DCT, or in short DA DCT, known as DA DCT. So, since it is twice the length of the x of n, so as you see, this is the definition of the DCT. So, since it is twice the length of the x of n, so 2 x of n, and if you take the cos of that part, cos of 2 pi by n into k n, since it is twice the length, so it is cos of pi k into twice n plus 1 divided by twice n. Okay. So, this is the definition of the DCT, and from which you can get back again inverse DCT, that is x of n you can get back from the DCT like this formula. So, here there is a constant term you will get alpha k, which is nothing but half for k 0 and 1 for all k other than 0, that is 1 through n minus 1. Okay. So, this is what is DCT. Detail again I will do it later on in my next consecutive video lectures. Here I am just trying to summarize the entire transformation part. Then like DCT there is one more transformation which is called discrete Walsh, W-A-L-S-H, discrete Walsh transform, DWT. Till now whatever be the transformation, that is DFT or DCT we have discussed, are based on the sine and cosine terms, but the Walsh transform is based on a rectangular function instead of sine and cosine. Okay? Rectangular waveforms rather than sinusoid. Suppose capital N is a 2 to the power m, then the discrete Walsh transform is defined like this: 1 by n summation over n is 0 to n minus 1 x of n. This is multiplication I 0 to m minus 1 minus 1 to the power b I n into b m minus 1 minus I of k. Okay. So, this is what is discrete Walsh transform. Okay. So, this actually represents the ith bit in the binary representation. Okay. Similarly, you can get back the x of n from the discrete Walsh transform using this. Similarly, there is another transform called Hadamard, H-A-D-A-M-A-R-D, Hadamard transform, discrete Hadamard transform, DHT. So, this is discrete Hadamard transform is also based on the rectangular waveform rather than the sinusoid. So, like if any capital N is equal to 2 to the power m, then discrete Hadamard transform is represented by this, something like discrete Walsh transform only, but instead of this b I, now it is summation over I 0 to m minus 1 b I n. Okay. And similarly, inverse Hadamard transform is this. Okay. So, these are actually different versions of the DFT only. The primary thing is the Fourier only. Now, go back to the Fourier again. So, in the Fourier, what I mentioned is an analogy that I mentioned. Suppose there is a wall, and behind the wall there are a few things that you have not seen. That means those are hidden. To see those things, you need to put a window on the wall and take the things, put the things together what you have seen. That means the entire wall is been broken and put one window. So, therefore, as you see here, in the DFT or DTFT or whatever, so basically DTFT, because theoretically it is DTFT, which is minus infinity to infinity. That means this window is of length infinite. So, what does it mean? It means whatever be the things you have seen behind the wall, you have seen all the things together. That means, if I asked you what you have seen first, what you have seen next, second, third, like that, you can't say, because you have seen all the things together, because the window is of infinite length. That means, mathematically or technically what we mean is, because of the infinite length window, the time domain information lost. You get the frequency domain information, but you have lost the time domain information. But we need actually both together, time and frequency together. So, now if we think of creating a finite length window instead of an infinite length window and sliding that window, instead of say one infinite length window, suppose I now install some number of finite length windows, then one window, finite length window, will be open at a time, then whatever be the things you have seen will be recorded. So, if you look at this formula, this window is of infinite length. Now, if we consider a finite length window instead of infinite length window, suppose 10, 15 different finite length windows are placed instead of infinite length window, and one window will be open at a time, and whatever be the things you have seen and put it together, then second window is open, and whatever you have seen for the second window you have put it together. So, that way if we do, then at least you can say that within that time range, this time to that time I have seen this, that time to that time I have seen this, like that. So, at least although it is not exactly at what time, but at least a range of time information will be retained. Okay. So, that is what is called short time Fourier transform, STFT. Okay. Short time Fourier transform. So, short time Fourier transform is nothing but the window function is being multiplied a finite length window over this is the window, and with a finite length W m. So, this summation is over minus m to m, but it is x of n minus m. Okay. So, this is the STFT. So, therefore, definitely short term Fourier transform is also a function of time. As I said, only x of e to the power j omega is the frequency domain information, where time domain information get lost. So, therefore, once it is STFT, you will get at least some range of time informations. Okay. So, that is what is STFT. So, then after that although this STFT, the window length is finite, but it is fixed. So, that means infinite, that whole infinite length window, now I am creating short time for this finite length windows, but this length, finite length is fixed. Okay. So, through this window what you have seen, suppose 2-3 things you have seen and you cannot distinguish now, but you can say that within this time to that time you have seen these things. So, that was STFT, but I want exactly at what time what you have seen, that is along with the time resolution. So, then what we need to do is we need to put a sliding window rather than a fixed length window, although it is a finite, but fixed in case of STFT, but I need a sliding window in case of a fixed length window. So, slightly it is sliding, the each of this fixed length window, I mean the short length window, finite length window will be sliding, and continuously you are recording what you have seen. That is, in that case you will get exactly at what time whatever be the things you have seen. That means, time and frequency will be retained. That means, frequency domain information along with the proper time resolution. That is what is called wavelet transform. So, that small sliding of the small finite sliding of the finite length window is being represented by a small wave. So, wavelet is nothing but a small wave. So, based on that wavelet transform. So, that wavelet transform is whole good for the continuous time case as well as discrete time case as well. So, in my next lecture, in another video lecture, I will explain detail about the wavelet transforms. So, here I am trying to cover up the basic of or the inside basics of the entire transformation that are required for the signal processing. Okay. Hope you understand, and if you have any doubt related to this, already I have shared the handwritten notes on the entire Fourier analysis, that is from only for discrete time, of course, this discrete time Fourier series, discrete time Fourier transform, discrete Fourier transform, and fast Fourier transform. So, along with the properties of all DTFS, properties of CK, DTFT, properties of x of e to the power j omega, DFT, properties of x of k, then FFT. Of course, FFT is an algorithm, so there is no need of that property, because it is just an algorithm of efficient calculation of DFT, and also the relationship between the Z. Okay. So, later on we will do the detailed explanation of all these transformation. Please go through this properly. You read all those things in any books, find out your queries and let me know your queries, or ask yourself some questions. If you have any doubt, you can contact me at any time. Thank you very much. Have a good day.